Welcome to AQA GCSE Chemistry 9 to 1. This is the final video, topic 10, using resources. Using the Earth's resources and sustainable development. Humans use the Earth's resources to provide warmth, shelter, food and transport. Natural resources, supplemented by agriculture, provide food, timber, clothing and fuels. Finite resources from the Earth's oceans and atmosphere are processed to provide energy and materials. Finite means that eventually we will run out of these resources. An estimate of the final amount of coal in the world as of 2003 was 113 years, 55 years of natural gas and 53 years of crude oil. Using the Earth's resources and sustainable development. Chemistry plays an important role in improving agricultural and industrial processes to provide new products and in sustainable development, which is the development that meets the needs of current generations without compromising the ability of future generations to meet their own needs. This graph shows estimates of if we continue to use resources, the world's resources, at the current rate, how many actual worlds would need to sustain that. The world average is that we are using 1.6 worlds Earth's resources at the moment, and you can see that some countries such as Australia and USA use a significantly greater amount of these. This is not sustainable because future generations will not have the same resources that we have because we're using them at a greater amount than we can replace them. Potable water. Water of appropriate quality is essential for life. For humans, drinking water should have sufficiently low levels of dissolved salts and microbes. Water is safe to drink is called potable. It is not pure water as in the chemical sense because it contains dissolved substances such as calcium, magnesium, sodium, potassium in this mineral water. In the UK, rain provides water in low levels of dissolved substances, we call fresh water, that collects in the ground and in lakes and reservoirs and rivers, and most potable water is produced by adding coagulants to it which stick sediment together, and the heavy particles then stick together and form large clumps. This water is allowed to settle in a tank and the heavy particles drop to the bottom, and these particles are scraped away to be used as fertiliser. You can then filter the water through layers of fine granulated materials. As the particles are removed, turbidity diminishes the water and clear water emerges. Turbidity is a scientific word for stirring. Part 4. To protect against bacteria which might remain inside the water, we add disinfectant in the form of chlorine, ozone or ultraviolet light. We maintain the pH by adding alkaline solutions to reduce corrosion to the pipework. Choosing an appropriate source of fresh water, passing water through filter beds and sterilising chlorine and ozone or ultraviolet light. You don't need to go into as much detail in the GCSE as they have in this image, but you do need to be able to go into this detail. Choose appropriate source of fresh water. So what you want to do is choose something which is as clean as possible. Pass it through a filter bed and then sterilise it. If supplies of fresh water are limited, desalination of salty water or seawater may be required. Now, desalinisation is a process that can occur through distillation, and this is a required practical that we're going to look at later in the video, or processes that use membranes such as reverse osmosis. Again, you don't need to know too much about the detail, just to let you know that in reverse osmosis, we add the salt water, and then water is pre-treated to remove any solids, and we adjust the pH level, and then we force water through membranes which stop the passage of salt to go through, and then the water is treated by stabilising the pH again. Desalinisation is not used in the UK because it requires high amounts of energy and therefore is expensive. Required practical 8, analysis and purification of water. Now you should have completed this practical where you take a warm sample of salt water, you place it in a conical flask with a bung and a delivery tube, which is heated by Bunsen and then delivers the steam, the boiled water, into an open flask, which is cooled, where the steam will condense into pure water. And we can test to see if the water is pure by boiling it. If it boils at 100 degrees Celsius and has a sharp boiling point, then we can test that. We can assume that it's pure water. We can also analyse the water by testing it with either cobalt chloride paper or anhydrous copper sulfate. Wastewater treatment. Sewage, agricultural wastewater, require the removal of organic matter and harmful microbes. Because the water is dirtier, it has more microbes within it. Industrial wastewater may require the removal of organic matter and harmful chemicals. Sewage treatment includes screening and grit removal. The wastewater and sewage is pumped through the underground into a lifting station where it's chemically treated and sent for separation. The separation filters out any larger solids than 30 millimetres, and this is transported to a refuge facility and buried. Settling basins allow heavy material to sink and to be scraped away. The waste is then fermented for 30 days and is used as fertiliser. The effluent, that's the remaining water, is then pumped into a bioreactor for 9 hours. Through a series of stages, bacteria break down the harmful matter and clean the water. Secondary clarifiers feed the water through bacteria to clean the water into drinkable water. Finally, the water is sterilised using either chlorine, ozone or ultraviolet light, and is balanced, pH balanced by adding alkali. So to recap, in the exam you need to be able to know the 4 stages: screening and grit removal, removing large materials, then sedimentation to produce sewage sludge and the effluent. The sewage sludge is removed in use of fertilisers. The effluent has to be further treated, that contains the water. We have anaerobic digestion of any further materials to form sewage sludge, and then we have aerobic biological treatment of the effluent. Alternative methods of extracting metals. The Earth's resources of metal ores are limited. In this graph we can see the world amount of copper available, and you can see that actually we have now peaked. There is less copper in the ground ready to extract than we've actually removed. Copper ores are becoming scarce, and new ways of extracting copper from low-grade ores include photomining and bioleaching. These methods avoid traditional mining methods of digging ores from the ground, moving and disposing of large amounts of rock. Phytomining uses plants to absorb metal compounds. They take them up in their roots. Then the plants are harvested and burned to produce ash, which contains the copper compounds. Bioleaching uses bacteria to produce leachate solutions that contain metal compounds. Metal compounds can be processed to obtain the metal. In both processes, hydrochloric acid is added to the copper compounds to form a copper sulfate solution, and then this can be purified either by using electrolysis or by using scrap iron in a displacement reaction. Life cycle assessments. Life cycle assessments, or LCAs, are carried out to assess the environmental impact of products in each of these stages. Extracting and processing raw materials. We've got raw material supply, transportation and manufacture. We then have construction, distribution, installation and use of the products installed, maintenance, repair, replacement, refurbishment. And then we have to consider the end of life, deconstruction, demolition, transportation or reuse or disposal. Use of water, resources, energy sources and production are some ways that are fairly easily quantified. Allocating numerical values to pollutant effects is less straightforward and requires judgment, so LCA is not a purely objective process. So it's easy to calculate for a specific product sometimes how much how much materials go into a product, how much energy is used in manufacture, packaging, distribution, use and end of life. But often it's difficult to consider how much CO2 is released during the whole process, or how much water is used, or the effect on land use or energy. Selective or abbreviated LCAs can be devised to evaluate products, but these can be misused to reach predetermined conclusions, for example in support or claims of advertising. So many advertisers might say that their manufacturer is carbon neutral, but then that doesn't consider CO2 release in transportation or maybe water use in the cleaning of the materials. Ways of reducing the use of resources. Reduction in use, reuse and recycling materials by end users reduces the use of limiting resources, use of energy sources, waste and environmental impacts. Metal, glass, building materials, clay ceramics and most plastics are produced from limited raw materials. Much of the energy for the processes comes from limited resources. Obtaining raw materials from the earth by quarrying and mining causes environmental impacts. Some products such as glass bottles can be reused. Glass bottles can be crushed and melted to make different glass products. Other products cannot be reused and so are recycled for a different use. Metals can be recycled by melting and recasting or reforming into different products. The amount of separation required for recycling depends on the material and the properties required for the final product. For example, some scrap steels can be added to iron from a blast furnace to reduce the amount of iron that needs to be extracted from iron ore. Corrosion and its prevention. This is a chemistry only topic. Corrosion is the destruction of materials by chemical reactions with substances in the environment. Rusting is an example of corrosion. Both air and water are necessary for iron to rust. Corrosion can be prevented by applying a coating that acts as a barrier, such as greasing, painting or electroplating. In this example, we can see that rusting has occurred because both air and water are present. In the second test tube, the water has been boiled and oil placed on the top, preventing any air or oxygen specifically to get in, and therefore, despite air being present, there is no rusting. Water being present, there is no rusting because oxygen is not present. In a third test tube, we have the same nail again with the bung placed to prevent any water vapour from the atmosphere to get in, and also we have anhydrous calcium chloride as a drying agent, and again we see no rusting because no water is present. Aluminium has an oxide layer that protects the metal from further corrosion, and unlike iron, which the oxide layer is porous and further water and oxygen get in and rusting continues, aluminium doesn't, and therefore doesn't require protection. Some coatings are reactive and contain a more reactive metal to provide sacrificial protection. For example, a layer of zinc is placed on top of steel, and because zinc is a more reactive metal, it forms a zinc oxide. Also protects the material if it's dented or scratched, because zinc will be oxidised preferentially to the steel. In fact, ships use this on their hulls to protect their hulls from oxidation and corrosion. Alloys as useful materials. Most metals in everyday use are alloys. For example, bronze is an alloy of copper and tin, brass is an alloy of copper and zinc, and gold used as jewellery is usually an alloy of silver, copper and zinc. And the proportion of gold in an alloy is measured in carats, 24 carats being 100% or pure gold, 18 being 75, 14 being 58 and 10 being 42. Now, silver and copper and zinc are added to increase the strength and durability of the gold and can also change the colour. Steels are alloys of iron that contain specific amounts of carbon and other metals. High carbon steel is very strong, as used in these drill bits, but can be brittle. Low carbon steel is softer and can be more easily shaped, for example, this braid. Steels containing chromium and nickel form stainless steel and are hard and resistant to corrosion. And aluminium alloys are used due to their high strength but low density, as used by the aircraft industry. Ceramics, polymers and composites. Most of the glass that we use is soda lime glass, made by heating sand, silicon dioxide, sodium carbonate and limestone. Borosilicate glass is made from sand, boron trioxide, which melts at higher temperatures than soda lime glass. Clay ceramics include pottery and bricks, which are made by shaping wet clay and then heating in a furnace. The properties of polymers depend on what monomers are made from and the conditions they are made under. For example, ethene forms polyethene, and when at low density it is branched so that the layers of the chains cannot pack closely together. We call this LDPE, or low density polyethene. High density polyethene is still made from ethene, but it forms unbranched chains which can pack very close together. And as a result, it makes it stronger and have a higher melting point. Thermo-softening polymers can melt when they're heated, whereas thermosetting polymers do not melt when they're heated. And this is due to, again, their design, where thermosetting have strong covalent bonds which link the polymer chains together and cross-links, whereas thermo-softening plastics do not have these cross-links and are only attracted by weak intermolecular bonds which can be broken by heating. Most composite materials are made from two materials, a matrix or binder surrounding and binding together fibres or fragments of other materials, which is called the reinforcement. For example, plywood. Plywood is a sandwich of wood fibres that are glued together, where the wood fibres run in one direction and then the second layer, the wood fibres run perpendicular to that, so therefore it increases the strength of the material. Concrete is very strong in compression, but not very good in tension, and so what we do is we put steel inside the concrete, which is very good in tension, and therefore you get the best of both the materials and it reinforces the concrete. And the last example here we have carbon fibre, where you've got the strength of graphite, but graphite can be very slippery as the layers can slide over each other, but this is reinforced by plastic, so it stops the fibres from moving over each other. It means that we can actually mould it into some very rigid shapes. The Haber process. The Haber process is used to manufacture ammonia, which can be used to produce nitrogen-based fertilisers. The raw materials are nitrogen, obtained from the air through fractional distillation, and hydrogen, which is obtained from natural gas or methane. The purified gases are passed over a catalyst of iron at high temperature, which is around 450 degrees C and 200 atmospheres pressures. Only a small proportion of the ammonia is actually formed. Most of the reaction mixture stays as hydrogen and nitrogen because the reaction is reversible. However, we pass the hot gas formed for the reactor into a condenser, and the small amount of ammonia that actually is made liquefies and is removed, and the gases will recycle back into the reactor. Production and uses of NPK fertilisers. Compounds of nitrogen, phosphorus and potassium are used as fertilisers to improve agricultural productivity. NPK fertilisers contain compounds of all three elements. Industrial production of NPK fertilisers are achieved using a variety of raw materials in several integrated processes. The NPK fertilisers are formulations of various salts containing an appropriate percentage of the elements for the farmer's needs, depending on what crop he wishes to grow. Ammonia can be used to manufacture ammonium salts and nitric acid. Potassium chloride, potassium sulfate and phosphate rock are obtained by mining, but phosphate rock cannot be used directly as a fertiliser, so it is treated with nitric acid or sulfuric acid to produce soluble salts that can be used as fertilisers.